All right, so this will be lesson 3 of Crypto Zombies, and we're going to be going over some more advanced Solidity concepts and some ways that differentiate Solidity from other languages like JavaScript and differentiate decentralized apps or dApps from, normal applications. So to start with, after you deploy a contract to Ethereum, it's immutable, right? So what that means is it can't be modified or updated ever again. So like the code that's out there, the functions that you have out there, they're out there and that's it. They're permanently out there. So the initial code you deploy to a contract is there to stay permanently on the blockchain. It's one reason that security is such a huge concern in Solidity. If there's a flaw in your code somewhere, there's no way to patch it later. And you would have to tell your users to start using a different contract address. And so that's something we're going to be going over in the next couple lessons, which is like how to set a contract address. Like if we have an upstream contract address that we're using, like what if it breaks, right? Or what if our contract, because remember all contracts when you instantiate them on the blockchain have their own address. So what if ours breaks? What do we do about that? And I can answer that really fast, and they answer it here, which is that we would actually have to, reinstantiate the blockchain with the fix, and we'd have to point our users to a different smart contract address that has that fix. But remember, this is also a feature of smart contracts, so the code is law. You can't kind of go in there and update everything, just whatever, or everybody can't, or I guess everybody could, but you want to implement your smart contract in such a way that everybody can't just do whatever, and change, like for instance this address here or some of the variables or something like that, storage. You want to write it in such a way that everything is secure. We will also go into how you could implement a backdoor. So while the code is law, you'll be able to see, like, if I develop a smart contract, I could easily leave something open that says, okay, I'm the owner, and I will be able to, set different variables. But again, I won't be able to really change like the code, right? I won't be able to like change functions, but although I might be able to like call different ones depending on if I'm calling it or not. So anyway, let's get into this. So in lesson 2, we hard-coded the CryptoKitties contract address, and that's what that is here. But again, what would happen if, it had a bug and, for instance, someone destroyed all of the CryptoKitties that are in there? Well, our downstream application, because we use this application, would break, and we would need to update this contract address with whatever bug fix that they implement. So it often makes sense to have functions that will allow you to update key portions of the decentralized app. But, who updates that, right? And we'll get into that in later chapters of this particular lesson. So for example, instead of hard coding the CryptoKitties contract address into our decentralized application, we should probably have a setKitty contract address function that lets us change the address in the future in case something happens to the contract, right? So we want to be able to update this. All right, so let's implement that now. What we're going to do is we're just going to get rid of this line here. And what we're going to do too is instead of, we don't have this address anymore, right? So we just want to have this instantiated here and ready to go, or not even really instantiated. It's just a variable that we can instantiate with our function. So what we're going to do is write that function or method right here, and that will be called set kitty contact address. And we actually want to put the function keyword here. All right, and let's come over here now. And what does this take in? It takes in an address, and you can see that here, and this will be the CryptoKitties address, and we'll call that underscore address. Now this will also be an external function, so basically the only way to interact with this function will be like outside of this contract. So there will not be another function or method from a different contract would not be able to call this. You'd have to call it from outside of the contract. So that's the difference between external and public, right? Public, you would be able to call from within the contract or outside of the contract. All right, so let's create a function. We already created the function. It's external. And what we're going to do next is we're actually going to set this kitty contract variable here to the kitty interface. This is basically the same as we did before, but instead we're just going to put address because now address is a variable. So it could be any CryptoKitties address, depending on if that needed to be updated in the future. All right. Now, it also says if you notice a security hole with this function, don't worry, they'll fix it in the next chapter, and we'll go over that. Let's see, we did something wrong here. So kitty contract, I think we need to do equals. All right. Okay, so ownable contracts. So this is kind of the issue with this, right? So the issue is that anyone can call this function, right? Not just you, the guy who created the contract. And it also kind of shows you that, this is a way I can create a backdoor, right? So if I'm the owner of the contract, what I can do, and you'll see throughout this, is I can make sure that that method we created earlier, this set kitty contract address, can only be called by me. But if I'm malicious and I want to break everything, I totally could now, right? Because I have a backdoor into this program. So watch out for this. This is actually, pretty. It's so used all over the place that you'll see that we actually have this ownable code that people use from OpenZeppelin, which is a Solidity library, and people use this so often they just pull it down, and you'll see what it is. It's called a modifier, and they could do anything. Let's see if they go over that here. I don't know if they go over it later, but basically you could imagine that if anyone wanted to basically have a function in here that says only the owner can call it, and it sends all of the Ethereum in this contract or from all addresses or whatever into that owner's wallet, right? They could do it. So this is the reason you want to audit a smart contract before you interact with it. All right, so below is the ownable contract. This one right here. And like I said, it's from the OpenZeppelin Solidity library. OpenZeppelin is a library of secure and community vetted smart contracts that you can use in your decentralized application. And after this lesson, they recommend we go check it out. Give the contract below a read through so we can, read through this. Basically, you can see there's an event here. We went over events in the first lesson. Events are just to let Web3.js or something know, or whatever know that something happens. So you can see that we emit this event in the constructor, right? So the ownable constructor sets the original owner of the contract to whatever the account is. So remember that message.sender is whoever's interacting currently with the smart contract. So this is how we get, or at least right now, how we will also be able to transfer ownership, because you can imagine too, if I want this contract to live on and I want someone else to own it, I can just, transfer the ownership over to them. All right, so let's see. Return the address of the owner. This just returns that. Throws if called by any other account than the owner. So now everybody, if I implement this modifier, because this is the modifier part right here, right? The only owner. If somebody else tries to do this, what will happen is it'll check is owner. We'll go to the is owner here. We'll say is message.sender, which is them trying to call it. Is that equal to owner? We'll have owner up here, which is was set initially by me, the first person who called it, or whoever created their instantiated this smart contract, right? We'll check if that's them, and if it isn't, then we fail fast, and we just say, okay, you can't run this method. All right, and this is renouncing ownership, transferring ownership, and I guess this actually does the transfer of the ownership here. All right, so constructors function ownable as a constructor. I think we went over that. The modifier is only owner. So the modifier, you can kind of think of a modifier, the way I think about it, is like a decorator in Python or something like that, or like an annotation or something. It's a little bit different, but we'll kind of go over that. And then there's this special syntax of the underscore, which just what that means is it means, run the rest of your function. So we're going to be putting this on a function, and you'll see in the code in a minute. We're going to be putting this on a function, and then this, and it's usually just some require to check if something's true. And then after that, we're going to use this to run the rest of the function after we do whatever check or whatever we need to do in our modifier. All right. So the ownable contract basically does the following. When a contract is created, the constructor sets the owner to message.sender, the guy who deployed it, which in this case I guess would be me, and it adds an only owner modifier which can restrict access to certain functions, which is basically, you know, what I said, but in a nutshell. It allows the transfer. Yeah, we went over transfer. And this is so common and all over the place that, you know, it's in this library. And most people just copy and paste the ownable contract out of the library. All right, so let's put it to the test. We've gone ahead and copied the code. So that's this right here. Let's go ahead and make the zombie factory inherit from it. So zombie factory, we just want to say is ownable. Did I spell that right? Yeah, ownable. And now that it's ownable, remember that zombie, we also need to actually import it. So let's do import and /ownable.sol and put a semicolon. And so remember that zombie feeding, what we created in the other, I think lesson 2, we did zombie feeding. It is zombie factory, right? Which means that it inherits from zombie factory. And since it inherits from zombie factory, it also, you know, by the transitive property here, inherits from ownable. All right, so that's pretty much all you needed to do for that part. There will be just lots of explanations in this. There's not really that much code to write, believe it or not, in all of these chapters. Now that our base contract zombie factory inherits from ownable, we can use the only owner function modifier in zombie feeding as well. This is because, yeah, this is basically what I was telling you. Function modifiers. Function modifier looks just like a function, but uses the keyword modifier. You can see that basically it does look like a function here, like this, but it's subtly a modifier instead of a function. But it does behave a lot like a function, you'll see. But it can't be called directly. It'll have to be used on a function, and you'll see what the syntax like that looks like. All right, so let's go down here and notice the only owner modifier on the renounce ownership function. When you call renounce ownership, the code inside only owner executes first. Then when it hits that statement in the only owner, it goes back and executes this. So you'll see, okay. And renounce ownership, we actually, inside of this contract, use this modifier that's right here. So when you call transfer ownership, which is public, the first thing it's going to check is that it's the owner transferring, right? Otherwise, anyone would be able to transfer. So we're saying, okay, require that it is owner, and then you can go run the rest of the function here. The rest of the function is transfer ownership, and then this gets called, and it transfers the ownership over to the address that you choose. All right, so while there are other ways you can use modifiers, one of the most common use cases is to add a quick require, and I think I went over that. They're basically just like if checks, you know, like if this, then you can do this stuff. Otherwise, it'll throw an exception. And let's see. And I think I went over this before, you know, contract owners have special powers, right? And they could add a backdoor. So this is something I really want to harp on because, you know, you can... If you interact with smart contracts, which I'm assuming you do, if you're going over Solidity, you're probably not just programming Solidity. You probably are invested in some way in some Ethereum contract or some Ethereum, or like Ethereum itself. But if you're, or just using DeFi or something, and a lot of people have lost a lot of money getting rug pulled in DeFi. So it's something, you know, before you use any of this stuff, make sure it's vetted by someone you trust or go read the code. And let's see. So now all we have to do is add only owner, the modifier, to the setKitty contract contract address. All right. So only owner. And I think I put 2 N's there. Yeah. So that's pretty much it, and you can see like that's what this does here. So it'll come after the access modifier there, and we'll put only owner. So when you call this, it had to be the guy who deployed this contract the first time. All right, so now we're going to talk about gas. Now gas is, I'll kind of just let them explain it here. So now that we know how to update key portions of the decentralized app as the owner, while preventing users from messing with our contracts, Let's also talk about gas. So applications on Solidity cost money to run, or they cost Ether, which costs money, like US dollars, I guess, right now, to run. In Solidity, your users have to pay, like I said, every single time they execute a function on your decentralized app using a currency called gas. We'll call it gas, right? Users buy gas with Ether, which is the currency on Ethereum. So your users have to spend Ether in order to execute functions on your decentralized application. How much gas is required to execute like a particular function depends on like how complex your function is, right? So each individual operation has some gas cost. You can look this up. I don't have like a link to it right now, but there you can get a rough idea of the complexity of some function and how much gas it will cost. So you really need to think about optimizing your code more so than a lot of other languages or applications, because this is really going to cost people money rather than just like a couple seconds or something like that, or even a couple minutes, right? And also you also should keep in mind, and we'll kind of keep harping on this, that writing to storage is more expensive than doing a lot of things, right? So just writing to storage, which is writing to the blockchain, is a lot more expensive than adding two integers, but it's also a lot more expensive than doing like most things. So yeah, I think I went over that. So why is gas necessary? So Ethereum's like a big, slow, but extremely secure computer, right? So the way that Ethereum is like a big computer is that basically it's running on a ton of different nodes, and you could be a node, maybe you are a node on the Ethereum network if you're running some particular code to be an Ethereum node. But that makes it extremely secure, that basically everybody is providing some amount of compute power to be a node on the network. So basically that code has to run on every single node before it's like confirmed, right? And this is what kind of makes it slow. But it for a lot of people, especially when you're interacting with DeFi protocols, you don't necessarily care if it's that slow. You care way more about the security than you do about a certain amount of speed. So when you execute a function, every single node on the network, again, needs to run that function. This is also what makes Ethereum very decentralized and censorship resistant. I'm sure someone can clog up the network with an infinite loop. Right, so imagine that you run an infinite loop on the network, or you run a ton of different infinite loops on the network, right? Eventually, you will run out of resources. You will run out of Ether to run that infinite loop. So you could sit here and run your infinite loop, but all you're doing is paying miners, right? Or paying stakers or something like that. So eventually, you will run out of money, and then everyone will not care that you ran that infinite loop because they will have all have gotten paid. Now they're just going to shill their blockchain here, which is, I'm sure, great. Let's see. We're also going to go over something called Struct Packing. Let's see. Basically, Struct Packing. All right, so basically, if you put int32 next to int32, and the only place where this really matters is inside of structs, because if we use a uint8 in like a function, like if I made this a uint8 or something like that, or a 32, it wouldn't care. It would still reserve the 256 space. But if I did that in a struct, like if I put this as like 32, it would respect that and only put 32. I think it's bits or bytes or whatever. I don't know right off the top of my head. So basically that's something that will work for you if you put 32 here. Now, if you put another unsigned integer, 32, directly under it, right? It'll work to even save more space. So let's see where they go into that. Pack variables together. You also want to, here we go. So clustering identical data types. So you'll want to put them next to each other in the struct, which can minimize the required storage space. So if we put uint32 next to another uint32, like another thing, actually it does want us to add data here. We're going to add two new features, one called level and one ready time. So we're actually not going to change that, but we'll do level, right? and the other one will be ready time. So let's add these here and then I'll talk about it. So ready time, right? And so what this is going to do is, because they're right next to each other, you'll save even more space. But say you took this and you put it like here and they're broken up, that will be unoptimal for you. So you will actually want to cluster identical data types next to each other like this. All right, so 32 bits is more than enough to hold the zombie's level and timestamp. It'll also save us some gas by packing the data more tightly than using a regular 256-bit uint. All right. So now we're going to talk about time units. We're also going to be going, like, I guess, a brief idea or history of epoch time or Linux epoch time. All right, so the level property is pretty self-explanatory. That's just going to be the level of our zombie, and then ready time is going to be the amount of time that we wait until our zombie can attack or feed on something again. So let's see, the goal is to add a cooldown period. So that's what ready time will be. So after a particular amount of time, that will be the cooldown, and then we'll be able to do something again. If you could just do things as often as you wanted, the game would be, as they say, too easy. All right, so time units. So Solidity provides some native units for dealing with time. The variable now will return the current Unix timestamp of the latest block. So the number of seconds that have passed since, so this is what the Unix epoch time is, right? So if you see this number, this is the total amount of seconds which have passed since January 1st, 1970. At least as this guy was writing it, it's something different right now. And this is just kind of a note. So traditionally, it's stored as a 32-bit number. And there will be a year 2038 problem. So this is when it will kind of overflow. 32 bits won't be enough to hold all of these seconds, right? So, year 2038, we overflow and some legacy systems will break. So if you don't want to be a legacy system, all you need to do is make your unsigned integer a 64-bit number instead, and you'll have ample space to hold a lot more time. But remember that if you did make it 64 bits, then your users would have to spend more gas to use your decentralized app. So do you expect your decentralized app will last past 2038? That's probably something you need to decide. But remember, your contract is immutable, right? So you can't go in there and change this data type in the future to 64. So unless you want to, move everybody over to a new contract, but let's say you have, millions and millions of users, do you really want to do that? But the problem is, all the way up until 2038, you're going to be spending extra gas. So it's, it's a trade-off. It's a design decision. All right, so let's see. So Solidity also contains time units like seconds, minutes, hours, days. I won't go into all the conversions between them, but, something to keep in mind. Like now is a keyword that holds, the epoch time of right now. All right, so this is how we're going to use these time units to implement this cooldown feature. So let's put it to the test. What we're going to do is, let's see, make it so the zombies have to wait 1 day after attacking or feeding to attack again. All right, so let's declare an unsigned integer called cooldown time. So we're going to do that here. We're going to say uint cooldown time. And we're going to set it equal to 1 days. I think that's the syntax. You might be tempted to put the number right here, but I'm pretty sure it's 1 days that you need to put there. All right, since we added a level and a ready time to our zombie struct in the previous chapter, we need to update create zombie to use the correct number of arguments when we create a new zombie struct. So that will be here. And what do we have? We have level and we have ready time. So let's see. What we're going to want to do for that is, for level, we're going to put 1 because when you initially create a zombie, when you push it to the zombies array, it will be of level 1. And the other thing we're going to do is we're going to cast, we're going to use casting here, typecasting, and we're going to make sure that it's an unsigned integer 32, and we're going to do now plus the cooldown time. All right, so the time that it is now plus whatever cooldown time that we decide on, right? So now what we're going to do is, yep, we talk about that. And now plus cooldown time will equal the current Unix timestamp in seconds plus the number of seconds in 1 day, which will, because remember so we set the cooldown time equal to 1 day. So it'll say, okay, whatever time it is right now after you created the zombie, and then this cooldown time before we can do anything, which would be a day. All right, so we'll implement the functionality to limit actions based on ready time in the next chapter. And we have something wrong here. U in cooldown time, and we're going to say that that equals 1 days. Okay. So chapter 6, zombie cooldowns. Now that we have a ready time property on our zombie struct, let's jump to zombie feeding .sol and implement a cooldown timer. Okay, so we're going to modify our feed and multiply function such that feeding triggers a zombie's cooldown, and zombies can feed on kitties until the cooldown period has passed. All right, so this will make it so zombies can't just feed on unlimited kitties and multiply basically all day, right? In the future, when we add battle functionality, we'll make it so attacking other zombies also relies on the cooldown. So we're going to feed on kitties, and that will be based on cooldown, and so will in the future attacking other zombies. All right, so first we're going to define some helper functions that let us set and check our zombies ready time. So let's take a look at these. Passing structs as arguments. I guess first we're going to want to talk about this. So we can pass a storage pointer, and remember, you can see that we specifically say when we pass strings that they're going to be memory, right? Now, we also can pass, instead of memory, we can pass storage here. And what that'll do is it'll give us an actual pointer to our zombie. So when we change something about that zombie inside of the function, it'll write it to the blockchain, right? And so that's why we're going to want to put storage there. Now, if we just did memory and we changed something about the zombie, it would change it in the function, and that's it, right? It wouldn't actually write it to the blockchain. So that's something to keep in mind, that if you do want to change something inside of the function, like actually on chain, then you're going to need to pass this storage keyword along with it instead of memory. All right, so let's put this to the test. Start by defining a trigger cooldown function. So where did it want us to do this? There should be a comment somewhere. I think here we go. All right, so we're going to say function, if I can spell it, function, and we want trigger cooldown. And let's see, what does this take in? It takes in a zombie, so we'll do zombie, right? Storage, and then I think underscore zombie. All right, and this will be internal. All right, so internal again just means that you can only call this function from within Solidity, and we also mark that with an underscore, which is just convention. You don't have to do that, but it's convention to, say that this function can only be called within the smart contract or within the contract, right? All right, so the function body should set the zombie ready time. So we're going to do, zombie dot ready time. Ready time, and where's that coming from? Let's go find out really fast. So right here, this ready time, which is in all zombie structs, right? So if we instantiate a zombie, we have the ready time, and we're going to set that equal to this right here. So we could probably literally just copy and paste this, and that will be casting it as a unsigned integer 32 now plus cooldown time. And remember, that's because it's an integer 32 here. And now plus cooldown time, remember now is whatever time that it is currently on the triggering cooldown. And cooldown time is this right here, which we instantiated, and it's a constant. All right. So next thing, create a function called isReady. So we'll do that right here. So we'll do function underscore isReady. And this function will also take a zombie storage. So we're going to do zombie storage. And we're going to, again, just call it zombie. And let's see. It will also be internal. It will be a view, which we'll talk about. And it will return a Boolean like that. All right. And the function body should return a, let's see, should return this right here. So it'll just return, you know, a Boolean, true or false. Is zombie ready time less than or equal to now? If it is less than, we can't really do anything. So, or let's see, yeah. So if it's, all right, if the ready time is less than now, let me think about that. Well, let me get it over there. Basically, what I do know, though, is that, let's see, we're going to do return, and then actually one more thing. We're going to need to put returns here to get that to work. All right, so this will return whether or not that the ready time is less than now. And then I guess if ready time is less than now, then it will return true. And then if ready time is greater than now, it will return false. All right, yeah, so yeah, because the ready time is the thing that's set on the blockchain. So we're going to need to get to that. So we're going to wait until now, which is whatever time it is eventually greater than that. And when it is, then we can do something again. All right, so that's, for some reason, that wasn't making sense in my head. All right, so let's check this, and we got that right. Okay, so Chapter 7, Public Functions and Security. So now let's modify feed and multiply to take our cooldown timer into account. So our, let's see, feed and multiply. Let's see, feed and multiply. Where was feed and multiply again? Blah, blah, blah. Oh, yeah, it's going to be in here. Okay, great. So that's this function here. That's this big function right here, which you'll remember that we did a lot of this in lesson 2. All right, so looking back at this function, you can see that we made it public in a previous lesson. An important security practice is to examine all your public and external functions and try to think of ways that other users might abuse them. So remember, unless these functions have a modifier like only owner, then any user can call them and pass them any data they want. So any user could call this function right now, and they could find this out by inspecting your code and find out like, hey, I can call this if I want to. So re-examining this particular function, the user could call the function directly and pass in any target DNA or species they want to. And so we want them to follow the rules, so we don't want them to just be able to pass in whatever they want. So what we find is that on closer inspection that this function needs to be called only by feed on kitty. So the easiest way to prevent this is to just mark it internal. So we're going to just mark this internal now. And I don't think they want us to update and put an underscore in front of it. So we're just going to leave it the way that it is, but I would typically think that you would put an underscore in front of it to mark that it's, I think internal and private should maybe both have underscores. Maybe not. I don't know. Yeah, like this one does, so it's something to think about. But I don't think that they do that here. All right. Right, because we don't want them to be able to pass any DNA that they want. Let's make feed and multiply take our cooldown time into account. So first, after we look up my zombie, let's add a require statement that checks is ready and passes my zombie to it. This way, the user can only execute this function if the zombie's cooldown time is over. All right, so you remember is ready, what it does is it takes a zombie and then it just checks if the cooldown time is ready to go. So what we're going to do is here, we already made this internal, we're going to do that right here. So we got our zombie here, and what we're going to do is we're going to do require that this function return true. So let's put this here, and then let's do is ready. Okay, and what we're going to do now is pass it our zombie, and that is called my zombie. And that's pretty much all we have to do, is say that our zombie is ready. If it's not ready, then we're going to just throw an error here saying that basically you can't do the rest of this. All right, and so we have that require statement now, and at the end of the function call, let's trigger the cooldown, trigger cooldown my zombie, so that the feeding triggers the zombie's cooldown time. All right, so we'll talk about what that does in a second. I think we could literally just copy this here and paste that there. All right, and so what does this do? Trigger cooldown time. Basically, the ready time will be equal to now plus the cooldown time, which we remember is 1 day. So it's just basically resetting the cooldown time. All right. So chapter 8, more on function modifiers. All right, so we're going to go a little bit more in depth. We're actually going to write our own function modifier here. So our zombie has a functional cooldown timer now. So basically, it has to wait a day after doing something. Next, we're going to add some additional helper methods, which we created a new file. So you can see they created this file called zombiehelper.sol here for us. And we've created a new file to blah, 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 which imports zombiefeeding.sol. See that it imports this right here. And zombie helper is zombie feeding, which by, that makes zombie helper a zombie factory. And it also makes it ownable. So it's something to think about, right? So previously we looked at a simple example of only owner, but function modifiers can also take arguments. So let's see this here. So we have a mapping, which is a uint to a uint. And we're going to say that a mapping to store a user's age, where a user, I guess, is represented by an unsigned integer, and their age is here. So a modifier that requires this user to be older than a certain age. So we're going to check if the user age is greater than, I guess the first thing will be the age, the second thing will be the user ID. And we're going to say age, which is this. It'll get the user ID, which will be the second thing passed. And we're going to find out if it's older than, some age that's passed here. So we're going to say older than, and we're going to pass 16 here. And if you're older than 16, you can do whatever this function logic here would be. In their instance here, this would be used to find out if someone could drive a car or not, at least in the US. All right, so you can see that the older than modifier takes arguments just like the function does. So yeah, see how it's a lot like a function here? Like it looks a lot like a function. It takes things in, it does all that kind of stuff, but it's like a function that is, again, modifying some other function. It can't just be called. It has to be in the signature of some other function. That's how it's called. And it also has access to the same things you'll be calling the function with. And you could also just hard code values in here, like this 16 here. All right, so let's try making our own modifier that will use the zombie's level property to restrict access to special abilities. So you could think like your zombie levels up, it gets new special abilities, right? So in the zombie helper, we're going to create a modifier called above level. So let's do modifier above level, right? And it'll take 2 arguments. So the arguments will be level, which is an unsigned integer, and we'll do level, and another one here for zombie ID. So we have the zombie ID and its level that we're passing in here. Okay, and we'll do this. Now the body should have a check to make sure that this level is greater than that. So what we can do is we can just copy and paste this here. So we'll just grab that. And actually, I think what we're going to want to do is put a require around it. So, because remember, most of these, most modifiers are just requires, right? So we're going to do that, and we'll just close the require here. And we just want to make sure that it is greater than, I guess, or equal to the level that we passed. Level. All right. That should be it. No, the modifier, there's something wrong with our above level modifier here. Let's take a look. We have above level, we called it that. Okay, we'll take 2 arguments, these guys here. And I think actually what we forgot to do was, this third step here, which is the last line so that it can call the rest of the function. So that is important. Remember not to leave that out. I guess that's something simple you could kind of forget to put there. We still have something wrong. We have the require statement dot level is greater than or equal to this here. Is there any, sometimes I feel like this isn't super helpful. So modifier above level, that is greater than or equal to All right, so I don't really know. Let's find out. Okay, so, oh, I called it just zombie. I should have called it zombie ID. There you go. All right, so next one. So zombie modifiers. Now let's use our above level modifier to create some functions. So our game will have some incentives for people to level up their zombies. If you have a level 2 and higher, you'll be able to change your name. And if you have level 20 and higher, you'll be able to give your zombie a custom DNA. So remember, giving your zombie a custom DNA will give it a custom look. So you can change it to whatever you want. And you could change like your different head or color or eye color or whatever else, right? You could probably, I guess, even make it a kitty if you put the 99 at the end. All right, so we'll implement these functions below and have example code from the previous lesson for reference. All right. Yeah. Okay. So let's put this to the test. Create a function called change name. So we'll do that here. So we're going to do function change name. All right, and this will take 2 arguments. A zombie ID, which we will remember to put the ID this time. So zombie ID, and then a new name. So we're going to put new name here, and this will actually be of type string. And we're actually going to call this call data and not memory this time. And they don't really go into why we do that. So it's just a string with the data location set to call data. Yeah, they don't really go over that, so I guess I won't, dive into why that is. But you can look up, I guess, what call data does different. Maybe they do. Okay, here we go. Okay, they say note call data is somehow, I think they might mean somewhat, but call data is somehow similar to memory, but it's only available to external functions. So I guess it's preferable when you're using an external function to use call data instead of memory, but don't quote me on that. All right, so I guess this does need to be external, which it says it is right there. And it should have the above level modifier. So we're actually going to pass the above level modifier here. And what do we need to do for that? We're going to put a 2 there. And then we're also going to need to pass it, because it takes a level and a zombie ID, we're going to need to do zombie. I think this actually should have an underscore in front of it. That would have been good to mess that up right after I messed that up the last time. So, all right, zombie ID, and then we'll open it here. So in this function, we first need to verify that message.sender is equal to the zombie owner. So remember that over here we have a mapping, which is like a dictionary, which says like, okay, I'm getting a zombie, let me go get the owner, right? And the owner is a contract address, or not a contract address, but an address, right? So that's something to keep in mind. So let's do that first. So we'll do a require statement, or let's see, require, and we'll put that there. So require message.sender is equal to, and we'll just copy and paste this here. So you can't do this unless you are the owner of this zombie. Okay, and then the function should set zombie dot name equal to new name. Okay, so we'll do that here. Okay, and we'll set that equal to underscore new name, the name that we passed. So we're going to be setting that name equal to new name. All right, and remember that is storage. We're not passing a zombie through here. We're actually just referencing the zombie array, and we're setting the name that way, so we don't like, I guess it's easy to kind of, I don't know, maybe you didn't like see that weird in your head, but that's something just to kind of remember, that this is actually a storage zombie by default, because it's a field over here inside of the zombies array. All right, so we're going to do another function. So this one's going to be called change name, but we're going to do another one that's basically going to be a copy and paste job with a few differences. And this one will be called change DNA. So DNA, and it's going to have the same zombie ID, but instead of new name, we're going to have new DNA, or let's see. Yeah, new DNA. like that. I don't know. Yeah, actually, I think this should be a capital N. Okay. And probably this needs to be a capital N as well. All right, so now instead we're doing zombie ID, we're doing new DNA, and then you can only change the DNA if you're above level 20. And message.sender, again, we're going to want to make sure we're, actually owning the zombie. And then instead of name, we're going to do DNA, and we're going to set that to new DNA. And remember, DNA and all this kind of stuff, it comes from the struct here, so it has a DNA attribute, and these zombies live inside this array, right? And a zombie ID is just 0, 1, 2, 3, 4, 5, 6, 7, 8 to infinity of this dynamic array. So a zombie ID is just saying some index of this array, and then zombies live in it, so that's how we're getting access to the DNA. So we have a zombie ID, which is maybe the 5th zombie in the array, and then we're just getting its .dna there and sending it to some new DNA, which happens on chain. All right, so let's check the answer. I'm sure something was wrong there. We have string call data is wrong. So for which one? For new DNA? String call data. Is the other one wrong too? Instead of that, we have call data similar to memory. I think it does come after that, right? Maybe I'm missing something. Let's see what we have for memory and stuff like that. Maybe it's something like that. So let's come over here and we do string memory that. Yeah, it should be right. Let's see. So a string with the data location set to call data, make it external. We did all that. All right, let's see what we got wrong here. Oh, yeah. This isn't a string. DNA is not a string. It's an unsigned integer. So that was another thing that we needed to change from, I basically just copy and pasted this one to make it faster, but maybe I should have wrote it from scratch. But basically that's it. So this one, you'll be able to change the name if you're above a level 2. And for this one, you'll be able to change the DNA if you're above a level 20. All right. So the next thing is that, you also don't need call data because it's an unsigned integer. All right. All right, so chapter 10, saving gas with view functions. So you'll see that view functions are a little bit different than regular functions, and in that they basically don't cost gas. So let's see, we have some special abilities for high-level zombies. Let's add one more function to our decentralized application. It needs a method to view a user's entire zombie army. So basically, you're just going to do a get all for all of the zombies that are for a user, right? Or associated with a particular user. So this function will only need to read data from the blockchain. That's literally all it does, and that's why we can mark it a view function. View functions don't cost any gas, so they're kind of special in that regard. So it's a way to interact with the blockchain without having to spend any money. So if we ever get an opportunity to do something like this, it's usually a smart idea to implement this in this way. So they don't change anything on the blockchain. That's why, Vue doesn't do anything. So marking a function with Vue tells the web3.js, which is a library for JavaScript, that it only needs to query the local Ethereum node to run the function. It doesn't actually have to create a transaction on the blockchain, which again would need to be run on every single node, and it would cost gas. So we'll cover setting up web3.js in the future, I guess. Also, if a view function is called internally from another function, it still costs gas from the original function to execute, right? So, obviously that's not for free. All right, so let's put this to the test. Let's see, we're going to want to be able to display the entire zombie army on the web page using web3.js. This function's logic is a bit complicated, so over the next couple lessons, probably finishing out the entire lesson, or the next couple chapters finishing out the lesson, we'll be implementing this function. All right, so let's do get zombies by owner. So I'm going to do function get zombies by owner. Okay. And it'll take one argument, address owner. So that's all we really need to pass it, is just an address for the owner, and then you're going to get all the zombies back that that owner owns, right? Okay, so let's make it external. So we're going to make it external, and we're going to mark it as a view function. So we don't need any gas, and it will return and it will return an array, but it'll return an array that is dynamic in size. So you could have like 300 zombies, or 1,000 zombies, or 2 zombies, and it'll return that. All right, and also it's going to be marked as memory because this is not stored on the blockchain. Okay, so we're going to leave the function body empty for now, and I keep getting things wrong, like small things wrong. So function get zombies, address owner, blah, 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 and view int unsigned integer. This one's got to be silly. Let's see. So create a new function, get zombies by owner. That's what we have here. It will take one argument, an address named owner. That's what we have there. We'll make it an external view function. This is this, right? And it should return. That was the issue. Okay, so we need to put returns. I always forget that you need to put returns there. And it's not even return, it's returns. So I guess it makes sense that it's returns and not return. One of the more expensive operations in Solidity is using storage, and I think I talked about that earlier in this lesson. So, and in particular, writes to storage, right? So this is because every time you do a change to some piece of data, it's written permanently on the blockchain, and again, thousands of nodes across the world, and this is something to keep in mind for sure. So just keep drilling it into your mind that when you use storage, thousands of nodes are going to have to run to put that onto the blockchain. So, keep that in mind. In order to keep costs down, you want to avoid doing this, whenever possible, unless it's absolutely necessary. Sometimes this involves seemingly inefficient programming logic, things like, for loops and things like that. Or like rebuilding an array in memory, right? So we're for looping through something and rebuilding the array in memory. Every single time a function is called, instead of saving that array in a variable for quick lookups. But ultimately, this keeps us from having to interact with the storage. Or interacting with doing anything with the actual chain. So in most programming language, looping over a large data set is extremely expensive. And remember, we're about to loop over like a very big, array. So keep that in mind. Like, it's really inefficient, I guess, to do something like this. And it's still more efficient than interacting with storage. Or, cheaper than using storage. All right, so let's see. Because, again, these functions don't cost the user any gas. And gas costs real money. So we'll go over for loops in the next chapter. But for now, let's see how to declare arrays in memory. All right, so this is going to be just a simple function here about declaring arrays in memory. So you can use the memory keyword with arrays to create a new array inside of a function without needing to write anything to the actual blockchain, right? So the array will only exist until the end of the function call, and it's a lot cheaper gas-wise than updating an array in storage. Free if it's using the view modifier here. All right, so here's how we're going to do that. Or just an implementation of doing that. So a function getArray, an external pure function. And so what we're going to do here is instantiate a new array with the length of 3. So you always have to actually give it a length when you do this. So that's something to keep in mind. Now, we're going to have our length, and you'll see that. But you are going to need to give it a length. And basically, other than that, it's kind of just like doing it normal. But you will also need this new keyword here. And if you're familiar with something like Java, then you're familiar with the new keyword. And it just basically means we're allocating some space for it. All right, so put some values to it, or in it, I guess. And so this is us just setting some values, and then you're just going to return this array called values. All right, again, they go over that it's a trivial example. It actually, let's see, so they currently cannot be resized like storage arrays can, and I guess we can't use arrays.push either. So we're actually going to have to, I guess, set it. So this is going, hence the for loop, because you can imagine we could have for looped over this. So this is going to be the need for the for loop in a future chapter, I guess the next chapter. All right, so let's declare a uint memory variable called result. So let's do a uint memory, and we're going to call it result. And what we're going to do is we're going to set it equal to a new. So we're going to say equals new uint array, and then we're going to need to give that some size. And I'm pretty sure we can just do this. Now, if you remember from lesson 1, we created this mapping here. And remember what we have access to here. We have access to the owner address. So we can pass in the owner address to some mapping that we have on the blockchain, which we're just reading from, right? And that's owner zombie count. So the owner zombie count is right here. We're mapping an address to the number of zombies that owner has. So this helps us allocate some space for our array here. Okay, and then I think we're just going to want to return result. Obviously, it has nothing in it, and it's just some allocated memory. And the issue here is we passed that there. We did this. We have uint memory result equals new, blah, blah, blah. I think, no, that this is the count, so it's a number there. We're going to say result equals new, and they do have that. We have the open thing there. Let's see. Called it result. Again, I wish they had something in here where they were like, oh, it's just blah, blah, blah. So let's see what we did wrong here. Uint memory result. Oh, again. All right, so here you go. Something simple. There you go. So you just had to make sure that it's actually an array. So there's probably times where you're watching me do this stuff and you see it as something simple. And I just use the answer thing because it's just faster than me going through and debugging this line. Because, I mean, if you program, you probably know that, like, if you're working through a problem and you see some small thing like this, it's just like you won't see it for a while. You'll like miss a semicolon, or you'll miss like making it an array or something like that, and you won't see it forever because it's an error you made. So, all right, chapter 12, for loops. In a previous chapter, we mentioned sometimes you're going to want to use a for loop. If you're familiar with any programming language, you probably know what a for loop is. So, again, we're going to talk about why we're going to want to build out the contents of this rather than simply saving some array to storage. All right, so for our get zombies by owner function, a naive implementation would be to store a mapping of owners to zombie armies in the zombie factory contract. So over here in the zombie factory contract, we could just basically do this. I don't know if it's going to let me type in here right now. I don't think it is yet. But imagine that we, took this mapping here and we put it under here. And instead of having this big, shared space where we have basically an address mapped to, or this is the count. So instead of having some zombie ID, which is really just an index in this array, so 0, 1, 2, 3, 4, 5, 6 into infinity, mapped to some address, right? Imagine that we just did something much simpler, right? This is how I would rather do it, right? I would rather have an address mapped to just an array of zombies, right? So then that way the owner, I could just look up the owner and then immediately get all the zombies. Boom, right? I don't need to read through all this. Whenever I have a new zombie, what I would do for an owner, what I would do is I would just add it to this mapping and have an array map to the owner. I don't know if that makes a lot of sense to you looking at this. I could probably draw it out, but this is a better way of doing it in my mind, right? But because we don't want to write to the blockchain for these kinds of things, we're going to want to avoid doing that. So every single time that we create a new zombie, again, we would just do this. So here's the problem with this approach. This approach is tempting for its simplicity, but let's look what happens if we later add a function to transfer. So we won't really see the error of this here, but here's where it becomes a problem. To transfer a zombie from one owner to another, which we will want to do, I guess, later in this lesson or maybe in another lesson. I don't know, because this one's coming to a close soon. That transfer function would need to do this. It would need to push the zombie to a new owner to zombie array. So we're going to need to transfer that to a different one. Then also what we're going to need to do is remove it from the old array. And here's kind of, I guess, a painful part, which is shifting every zombie in the old owner's array up one place to fill that hole. And then what we would need to do is to reduce the array length by 1. This is the extremely expensive thing, right? So I guess it would have to happen like n times or whatever. And so let's see. Yeah, so if an owner had 20 zombies and it gives one away, we would have to do 19 writes to maintain order, right? Now, I think that's the important part, is maintaining order. Yeah, so here you go. So this is the note. Of course, we could just remove the last zombie, right? And that would, it would be a lot easier. But then we would change the ordering of our zombie army every single time we made a trade. And maybe that's something you don't want to do. Maybe you want to keep it all in order. So yeah, so storage is expensive. I told you we were going to be harping on that in this video. All right, so since view functions don't cost gas, can be called externally we can simply use a for loop in order to get zombies by owner, or in get zombies by owner to iterate the entire zombie array and build an array of zombies that belong to this specific owner. So then our transfer function will be much cheaper since we don't need to reorder any arrays in storage, and somewhat counterintuitively, it is technically cheaper. So I hope a lot of that made sense. Maybe it didn't. It might make sense as you kind of work through all of this stuff. But yeah, so this is technically cheaper. So this is using for loops. This is like classic Java or like C++ for loop or something like that, right? If you're familiar with easier for loops, that's just like for blah in blah. Then this might look a little bit foreign to you, but most likely you've seen something like this before. So this is just, printing out everything between all the even numbers between, I guess, 1 or 2 and 10, right? So let's put this to the test. Let's finish our get zombies by owner function by writing a for loop that iterates through all the zombies in our decentralized application, compares their owner to see if we have a match. So remember, we're going through all the zombies, right? Like every single one. And I guess even still that is easier or less costly. Compares their owner to see if we have a match and pushes them to the result array before returning it. So let's get started here. I think we're going to want to be over here. Okay. So we're going to declare a uint called counter. Let's see if we can do this without any errors. And we're going to set that equal to 0. And we'll use this to keep track of the index in our result array. So we're going to start at 0, and then we're going to, just keep counting up. We're going to declare a for loop that does this. So we're going to say uint equals, or uint I. And I is just, it's kind of, I guess it stands for iterator or something like that. But most people just use I for iterate, I guess. And you've probably seen that before. So let's do I equals 0, and it's going to go all the way to less than zombies dot length. And the reason for that is because zombies dot length is like, remember we start an index at 0. So as we go through zombies dot length, we're going to go, say there's 5 things. We're going to want 0, 1, 2, 3, 4, which is 5 things. And so zombies dot length will be 5. So we're going to do 0 to 4, right? Because that is actually 5 elements. And this is the confusion of 0 indexing, but it's, something that if you program a lot, you're probably just used to. All right, now let's see. The next thing we're going to want to do is inside the for loop, we're going to want an if statement, which it says right here. And that checks if the zombie to owner is equal to the owner that was passed in here. So what we're going to do is we're just going to put this here. We're going to grab this. And then we're going to do, is it equal to owner? All right. Now, if it is the case, then what we'll do is add that zombie's ID to our result array by setting result counter equal to I. So we're going to do that. So result counter, or like result, which remember, all right, result will start at 0. And then what it'll do is it will add, that zombie to this new array, which is sized by the amount of zombies that this owner has. All right, so result at counter, which is obviously starts at 0, is going to be equal to, I guess just I, right? Because remember, we're going to be going through 0, 1, 2, 3, 4, 5, 6, 7, 8, all the way up to 30, and for instance, 30, and if there's 30, like, you would just get all the ones you own between like 0 and 30. Or if there's 100, all of the ones you own between 0 and 100, right? So you're going to skip the ones that you actually don't own. All right, and then inside here, only when this happens are we going to implement the counter. Okay. All right, so this is basically how we can return all of the zombies for a particular owner without spending any gas. All right, and I'm glad that one worked on the first try. So now we're going to be wrapping up. So they say, congratulations here. We're done with lesson 3. So to recap, we've added a way to update our CryptoKitties contract. We've learned to protect core functions with only owner. We learned about gas and different optimizations. We added levels and cooldowns to the zombie. We now have functions to update a zombie's name and DNA once the zombie gets above a certain level. And finally, we now have a function to return a user zombie army, which was, I guess, that last painful thing that we did there. So let's see, we upgraded our zombie, I guess, and now that no name, which was the name of the last one that we created in lesson 2, which I guess is this guy here, we can give him a name. Because we already have a name for the original zombie that I made. And so now we're gonna, in lesson 2, we created this cat zombie. You can see he has like a tail or whatever. And so we're gonna give him a name. Let's think of a name. I don't know, because I guess he's over, if he was over level 20, we could also change his DNA. But since he's in between 2 and 20, we can only change his name. So I don't know. Cat Chris. There you go. All right, we'll save that and we'll move on to the next thing here. So again, we're done with this one. I'm probably going to keep going through all of them. We'll tweet this out, I guess. All right. Okay. And let's see. I don't know how we can go back. All right, so that's pretty much it. This was kind of a longer, more involved lesson, so, good for you if you made it through the whole thing. I hope my explanations made sense. But yeah, so I'm just going to go over where you can find me. So basically in the description of this video, you can, I guess, donate crypto, but mostly I want to just point your attention to the different social media and places where you can find me. So this is my website here, and there's links to all this stuff in the description for the video. So my website is here with all my social media there. I'd rather you follow me over on Odyssey. It's like a crypto platform. It's kind of like a YouTube competitor. This is my GitHub if you want to go check that out and see some of the projects I'm working on. You can follow me on Twitter. Right now I'm basically just tweeting Crypto Zombies lessons. Sometimes I stream, and when I do, it's over on Twitch. And if you want to support the channel, you can support me over on Patreon. Alright, so that's pretty much it for this video, guys. If you liked it, make sure to like and subscribe.